machine learning algorithms requires some black art, which is not exactly found in textbooks. By black art, the author actually means inside knowledge from people who have been in the industry for long enough to know the tricks of the trade. So there are different types of machine learning. There's classification, regression, anomaly detection, and so on. Today we're going to talk mostly about classification because it is like the most widely used type of machine learning. So we're going to design learners. And what do we need to design learners? Learners essentially take a training set of example as the input and the output as a classifier. This is the step to designing a classifier. We design a classifier as such. So then the classifier in the future will take in unseen inputs and provide outputs for these unseen inputs. And one of the first uses of machine learning was spam filtering, checking whether incoming emails were spam based on some keywords in the email. So learning is a combination of three processes like representation, evaluation, and optimization. So there are thousands of machine learning algorithms available. How would we select one? The author tries to provide some insight into this using a three-step process. We should not get lost here. So the author says that there are three key components to this. One is representation. We choose the best hypothesis space. And what do we mean by a hypothesis space? We choose a space where there are a set of classifiers that can be applied to this problem. That is, if our training samples are instance-based, we go for a type of classifier or a set of classifiers. Then evaluation. Now we know that we're going to use these set of classifiers for this instance-based problem. And so how would we rank these classifiers? How would we evaluate? For example, in the task of machine translation, we could use a neural network, we could use a support vector machine, and we could use something else like a deep learning approach. How would we distinguish between the good and the bad here? There is a rogue score or a blue score we could use. Similarly, in the tasks of information retrieval, we could use something like the F1 score, we could use a discounted cumulative gain, and so on. So the author says we should choose a good evaluation metric that can provide a clear distinction between the good and the bad classifiers. And the next is optimization. That is, we find the highest scoring classifier. That is, given we have a set of classifiers, we have a good evaluation metric to like separate out the good and the bad. We want to optimize each classifier to give its best performance. That is, we find the highest scoring classifier. We do this by using, there's a continuous optimization the author talks about, the author tells there is a combinatorial optimization. It all depends on which representation we use. The representation leads to the optimization. In an instance-based approach like support vector machines, we would use a continuous optimization technique like quadratic programming. So what do you guys think? Which would be the best three, like pick one from each to use? What is the best combination? How would we determine the best combination? Yeah, it actually depends on the problem. Like this is the essence of the paper. The author tries to give us some inside information about the various nitty-gritties of machine learning, so that at the end we will have a better idea of picking one for each classifier. How would we know when we're getting started in this field? So it actually depends on the application.
Yeah. So the whole point of machine learning here is that it should be able to generalize upon the new unseen data, right? I mean, there's no point on learning on the same, on the same training set and then applying, all these things. So it's no better than tossing a coin, as the author mentions. But I mean, let's see here. What do you think? I mean, how could we generalize the model? I mean, what are actually the different ways of generalizing the models? Okay, let's start with that. What do you think?
As we discussed in the class, cross-validation can be one if you have less data.
Yes. So I mean, cross-validation. So I mean, what do we do in cross-validation? We keep, say like 10 folds, or 10 folds probably. So we keep like in one fold for the testing and the other 9 folds for the training, right? And we do it just repeatedly. All right. Okay. So I mean, that's one area that we could do. Anything else? Anything else?
I think there were a few more mentioned in the paper. Keep it that's the most common one.
Yeah, so that's the most common one. The other thing that could be there was,
your training data matters a lot, right?
Yeah.
So to generalize a model to various applications, your training data should be representative of the different scenarios where the model will be.
Yeah, exactly. So, I mean, that's one good point. And another thing is that we could actually, just keep a separate holdout set, right? So, I mean, that could be called a validation set, and we use that always, okay, for actually, doing all these kinds of validation, right? So, So we use cross-validation. But what are the different, where this whole idea of cross-validation can be misused? What do you think? This whole idea of cross-validation or keeping a validation set, this whole idea could be misused or misrepresented, basically.
If you use the validation set to train, it can go wrong.
To train?
Maybe use the test set to train your model. I don't know.
Yeah, but yeah.
When the validation set is like similar to the other 4 sets, like training set, it contains the same.
Well, one thing we need to make sure that, both the validation set and the training set should be a part of the same population. Okay, that's the most important thing. It should be represented. Representing the main population which is there, right? Like for example, if we have a model which is used to predict a risk of getting a disease. So if we have the training set probably of only males, right? And we have the validation set which is actually basically generalizing everything. So that's not a good thing to do, right? And any other instances where you think that it could be really a misuse?
If you would repeat the data.
Huh?
Maybe the data is skewed or every time you're using same kind of test data. Maybe.
Right, maybe. And another thing is that we can't use cross-validation in terms of a time series data. If you just keep that in mind. It's very difficult to use that. So, for example, if we have some kind of a stock exchange or a stock prediction data set, right? So we have it yearly, right? So if we have that as our training set, we can't use it as a folds. So for that case, we actually use a separate separate thing called the forward chaining, right? So let's not go into that. So and obviously that's that. So another thing that the author talks about is that the data alone is not enough. We need something more than data, right? So and that more, to be precise, is knowledge, right? We need some knowledge about the data. So it's like metadata, right? So if we know that our data has probabilistic estimates, we could probably use something like a probabilistic graphical models, right? If we know that our data is somewhat like a rule-based system, right? Like we have some kind of if-then rules, then we could use a decision tree, for example. So those things are there. And also we should actually thank our stars, because the data is not completely random. It's really specified in some portion of the data point. So if we consider everything, basically every space that's available, okay, of the whole dimensions, so it's really random. So you can't learn. So machine learning fails in those cases, but there are no such cases. Okay? So and yeah. So here's the thing. Here's actually the beauty of machine learning, that a small amount of input knowledge can actually result in a large amount of output knowledge, right? So, and as Lord Baelish says, okay, knowledge is power. So, here's a small video of Google's DeepMind. So what it uses is, reinforcement learning to actually learn a game, but it doesn't know anything about the game. All it knows is that is the screen, it has the screen, so it has the access to the screen, and it has to maximize a score on the screen, that's it. That's all it knows, right? So it just trains and trains and trains, and let's see what happens. Okay, there's no sound, by the way. So it's doing really poorly, as you can see. It's not doing anything at all. It doesn't know what to do. And on top, that's the score it wants to maximize. It's pretty cool, right? The coolest part is you have to come actually.
Here, this is where what we saw. A very small amount of input knowledge actually turns into a large amount of output knowledge. The only knowledge that the game actually had was that it had to maximize a particular score, and it had sensory input of something on the screen. And they described that the game actually has no knowledge of that there is a slider, there is a ball, you have to hit something, no knowledge. All it knew was that I have to maximize something, and it is given some information about the sensory input, that's all. And it learned and learned and learned, and it turned that small amount of input knowledge into this vast amount of output knowledge where it actually beats the game. It just needed like, what, 4 hours of training, I think, and then it beat the game. So this is the advantage of machine learning. One small amount of knowledge, it's like a nuclear reaction, you have like, you provide this small amount of uranium and it gives energy, it's like that. So the next issue that the author talks about is actually overfitting. We've all heard this buzzword, overfitting, overfitting. You should not overfit, you should not overfit. But what is this overfitting? The overfitting happens when the classifier actually gets confused. That means that the input data and the knowledge about the data is not sufficient for the classifier. Either the data is too much or too less. And it hallucinates the classifier. The classifier starts getting confused. It's like, oh my god, I don't know the sample, I'm not sure what the sample is. Or it continuously thinks that the sample is something else when it is probably the opposite class. So the author talks about the bias variance trade-off here, wherein an ideal classifier would have low bias and low variance. That is, it will get new things right all the time. There is no bias. And no variance, wherein it will learn the things that it is supposed to learn. But turns out that it is not exactly true in all cases. There gets a high bias where the classifier learns the same wrong thing repeatedly. There is a sample which just probably belongs to the no class, but the classifier keeps identifying it as yes class and it does not learn at all. That means it's like a very weak algorithm. And then the next is the case of high variance. For instance, we have a sample that says, see, I belong to the yes class. But the classifier learns everything about the sample except that it actually belongs to the yes class. Classifier learns, the sample has this color, the sample is this long, this big, or whatever. It learns the features of the sample, but it does not actually learn what class the sample belongs to. So, can you guys give me an example of a learner which has high bias and a learner which has high variance?
Which is actually prone to high bias.
Or prone, yeah, exactly, prone.
Maybe SVM.
SVM is what?
If a linear kernel SVM can go wrong, if it's not linearly separable,
Maybe, yeah. So it's kind of a linear learner, right? Yeah. Does it have high bias or high variance?
I mean, bias is low, I think. Oh, sorry, variance is low because either it's yes or it's no.
Yes or
It
no.
won't,
Yeah. So bias is high.
but variance is low.
Yeah. So where would we have high variance, or which learner is prone to high variance?
A decision tree, if you
Yeah, a decision tree is prone to high variance. If there are like, in the previous lecture we saw the example of whether the boy will go to play tennis or not. We had four conditions to learn from, but what if there are endless number of conditions? Whether the boy is like, there are so many conditions to learn that there's just too much variance sometimes that it actually misses out on whether the guy will actually go out to play tennis or not. This is where, so we desire for low bias, low variance, but there's often a trade-off. Like, we know that the decision tree is prone to high variance, but we still go for it in terms of rule-based classifiers because it's a trade-off there. We know that it will have low bias, and we probably know that we have some knowledge that very rarely will we encounter something which has, or a data set which has high variance. So there are many options to avoid overfitting, but we must proceed with a step of caution here. While trying to avoid overfitting, we should not underfit. We should try to balance it as much as possible. So there are many options we can do here. So one is we could use, in case of a decision tree, we could use cross-validation. We could use a cross-validation approach to identify the best decision tree to learn. That is, that the ordering of the rules. That we saw that one or two features actually played no role in the making of the decision at all. But how would we know that? It's a trial and error approach. So we try to use cross-validation, try different combinations with decision trees, nodes, and then figure out the best decision tree to learn. Another approach we could use is something called a regularization approach, where we add this parameter to the classifier, such that we penalize those classifiers which have very rigid structures, and avoid those classifiers which have lesser room to overfit. And the third option we could go for is like a chi-square test, like a statistical significance test. Like we have the sample before you apply, you add this new dimension maybe to it, and we have the sample after the new dimension. See how the distribution of the class changes after this using the statistical significance test, and go for either based on whichever is the best. Now, sometimes the author makes this remark that a more powerful learner is not necessarily better than a less powerful one. Sometimes a less powerful learner could be equally good or better than a low powerful learner. That is, David could actually stake Variance here. The next thing the author talks about is about intuition. It fails in high dimensions. We've all heard, like if you've ever done a course on machine learning, you've heard dimensionality. When you start doing support vector machines, you talk about a kernel function, put it into a higher dimension and all that. So what the author tries to tell is that we humans are constrained to think in 3 dimensions. The closest we ever got to the next dimension was by watching Interstellar. So the author tells us that we are constrained to think in a 3-dimensional space. And I mean, even Interstellar was kind of hard to imagine it, being time as a next dimension. It was, the movie tried to tell us something, but there was always this thing, actually, is it actually a dimension? So the author says that our assumptions and our idea of the world in a 3-dimension will not work in a higher dimensional space. But we actually cannot imagine that higher dimensional space because humans can only comprehend up to 3. So there we talk about the curse of dimensionality. What is the curse of dimensionality? There are samples in a lower dimensional space will be like, you can easily identify between them. But when you use the kernel function, put it onto higher space, they will lose all the difference. They will all look the same. That is the curse of dimensionality here. And we have this nice graph that says, for any machine learning problem, there is always an optimal number of features. And once you overstep the optimum, your classifier performance starts degenerating. And the goal, the secret to designing a good classifier is in figuring out this optimal number of features. And so are we doomed then? If we cannot think in that space, can we not design a classifier that works in that space? What do you guys think?
And we have warning problems of not being able to think about higher dimensional space. The whole field of behavioral economics is dealing with biases. We are actually in a linear space, we have problems figuring out numbers. So we are doomed as predictors for sure, but it's not necessary. Our intuition is incredibly biased because how our brain operates is incredibly biased.
Yeah.
So in that sense, we should not be doing predictions like that.
I mean, we work in a probabilistic world, so I mean, you can actually estimate to a reasonable level of probability that you can. I mean, you can't go extremely high dimensional, but you can go reasonably good in comparatively.
Actually, it turns out that as humans we might be doomed, but as humans who design machine learning algorithms, we are not doomed.
Yeah.
Because even though we can't think, there is some good aspects of machine learning. We enter here the thing to counter the curse of dimensionality called the blessing of non-uniformity, wherein examples are all never uniformly spread. They are more often than not concentrated in regions. That is like the essence of clustering also. Right? So we know that examples are always going to be concentrated in regions, and fortunately, in the initial stages of designing a learner, they will be concentrated in the lower dimensions. So we can use the knowledge of this concentration, like a region of convergence or something like that, to put these samples onto higher dimension, such that even in that higher dimension, they will still be concentrated. But they'll be concentrated more towards the lower dimensions. So it's something like figuring out the best kernel function, such that we don't lose track of our information. In the task of spoken language identification, maybe you could use a linear kernel. But turns out that an RBF kernel actually works better than a linear kernel here, because there are some samples which were not actually together in this one, but were together there. So that's the...
So the next thing is feature engineering, right? So, the author talks about the fact that feature engineering is the key, right? But what do you guys think? Do you think that feature engineering is the most important part of the whole aspect, or is it like data or algorithms?
One of the most important, maybe.
Yeah, all of them. Right?
All of the above. I think
all the
until
above,
now it has been, but now we have stuff that could learn the features on their own. So I think it's like a changing trend now.
Yeah, so basically this whole idea of deep learning actually, does that, right? So it's it's a debatable topic actually, but it is the most important part of the process.
Yeah, one of the aspects of like feature learning and representation learning, I think it's fantastic, but often so the world that we do research in often involves collaborations with psychologists and clinicians. So while we like to do feature learning right now and it's performing better, they still want us to communicate to them like what we actually observe, and it's kind of hard to do sometimes. So I just like to keep that in mind, that feature engineering is still valuable and viable, but the deep learning community is certainly moving away from that.
Yeah. So, and it's also an iterative process. The whole process of learning and validating. It's not a one-shot thing. Like you do it and then you're done. Okay, but I mean that's not how it goes. And yeah. And another thing that the author talks about is learning or combining models, right? So this is where ensemble classifiers come into the picture. So he talks about basically three types of ensemble classifiers, which is the boosting, bagging, and stacking. In bagging, the idea is like this. So it has a number of classifiers, and then it actually trains on a random variation of the training set, each one of them, it learns, and then you have a majority voting, right? So that's how it goes. And in boosting, you have a new classifier which learns from the previous mistakes that actually the previous classifier made, right? So it turns out that bagging is very good when you have a data with very high variance, because it actually lowers the variance there, because it's actually averaging out the whole thing, right? And in boosting, it's very good for high bias, right? And also we have stacking. So, but I mean these models are really really good, right? But why don't we use it all the time? Why ensemble models are not used all the time? I mean, why do we use stuff like SVM and all?
I mean, again, a powerful algo might not be as good as a simple algo, given the situation.
Okay.
So
okay.
It's too powerful maybe for the thing. Maybe.
Yeah, and so we got to wrap up for the next group, but also that's one of the reasons why, for example, boosting algorithms, they often have very, very poor algorithms that are just a tiny bit better than chance. Okay. So that's why they're called weak classifiers.
Yeah.
And so that's kind of one plan to alleviate that.
Yeah, so that's the thing. And another thing is that it runs very poorly on the test. I mean, like on, I'd say, the timing of the whole thing, right? So it takes a lot of test runtime because it goes through all these classifiers, right? And also it's a kind of black box. It's kind of going towards the deep learning way. So that's the reason.
Again, there are tricks for that.
Really? Right. So this was Netflix price.
So one of the final aspects the author talks about is simplicity.
But last slide.
So let's say we have two classifiers, which are, one is very complex, one is simple, and both have this similar test error rate. Which one is better?
Simple.
Well, it can be either, but which one would we prefer? We would prefer the simple one because simplicity as such is a virtue. So this is like one of the final aspects the author talks about. And the last thing that the author talks about is that correlation does not imply causation.
Yeah. So have you guys heard about the butterfly effect?
Okay.
Have you guys heard of the butterfly effect? Where does it go to?
That the author says use machine learning as a guide for action. Learn from data. The data will give us some insights. Use the insights to best engineer your something like that. Like let's say we know data shows that diapers and beer are bought together. Use the data as a guide, and maybe you could put these together in similar, the next to next in a supermarket.
Yeah, but one does not cause the other. So
it's just that use this information as like an investigative action. So
okay, done?
that's it. So the author says.
All right, next group. Sorry for that.
One more slide.
Good morning, everyone. My name is Priyanka, and we have Room over here.
Not wrong.
Yeah, I hope I got it right. Yes. So far in class, we have discussed about a lot of various machine learning algorithms involving classification, and then both supervised and unsupervised as well. So, but for a given data set, and how do we actually measure an algorithm? Well, I mean, measure the performance of an algorithm is basically today's topic of discussion, which is an introduction to ROC analysis, and ROC stands for Receiver Operator Characteristics. So before we move on, I want to just put a quick question. So basically, when you say measuring an algorithm, the first thing that comes to our mind is basically how accuracy would be the correct measure. I know it was covered in today's topic, but again, to reiterate on that fact, so why do you guys think accuracy is one of the good measures to measure an algorithm?
Let's just know about the error. Basically, we are trying to check whether our algorithm, how much error our algorithm has, and it's kind of a simple way of analyzing the algorithm because it gives us a value, either it is like high or low, and based on that we can make the analysis quicker.
Yes. So basically, because it's easy and it's simple to implement. But many times it so happens that, say for example, in your data set you have 80% of the cases which have negative value, and you have written some really complex algorithm which performs better, but it has lower accuracy, and you have just written a simple rule saying that just declare everything as negative, then obviously you get 80% as accuracy. So that is not a complete measure. So yes. So yeah, like I said, that is the biggest problem with the accuracy thing. So what are the other metrics that you think are helpful in evaluating the performance of an algorithm?
F1.
Yes, F1, precision, recall, and then of course ROC. So yeah, before we move on to today's topic, let's go through some terminologies so that we understand it in a better way. So we have, this is basically the confusion matrix. And then you have the, say for example, you have an instance. The capital Y and N are basically the predicted values, and the smaller P and N are the actual results. So along the first quadrant, over there you have true positives. Basically, if your accuracy is, I mean, if the actual value is correct and the predicted value is also true, it is true positive. Whereas if your actual value is positive, but your algorithm predicts it's negative, it's called as false negative because it's falsely predicting as negative. That's how I remember it. And then false positive is basically your actual value is negative, and then you predict as positive, so that's like falsely predicting it positive. And then negative and negative is again true negative. So, and along the columns we have something called as column total, so that is basically the total number of, it's represented by P and then N. So a couple of interesting metrics, like we have FP rate and TP rate. So true positive rate is basically the fraction of data sets which are actually true. So basically true positives by the column total of positive. And similarly the FP rate. So we have precision and recall as discussed, and then accuracy is basically the percentage of correct predictions over the total predictions. And then FP measure is basically your harmonic mean. So we take precision and then recall and then combine it. So what we get from that is basically your FP mean. FP measure, sorry. So moving on to the next slide. So the biggest example where you can use precision and recall is basically with the clinical data and information retrieval. And then combining precision and recall is your F1 score. Even if, could you tell me why even though we have precision and recall, it's not a complete measure. So can you guys think of some aspect related with respect to the search engines? Yeah, so we use precision and recall to measure the performance of a search engine. But that is not exactly a complete measure. There are something else which you can, add to it, and then you get a proper search engine.
Discounted cumulative gain, NDCG we could use.
Yes.
It kind of measures how the results are ranked with relevance to something else. So over a period of time we could track how the results are ranked, and we could capture user clicks to see which one they use, and use that to like modify use that knowledge to improve the search the next time and improve the NDCG score.
Yes, that's a good point. And so in addition, not only precision and recall, but say for example, if you have page ranking, we can always say rank what is the better result and display that one at the top, which we cannot get with precision and recall because we just get whether it's the correct answer or not.
Yeah, so I just want to say like precision, recall, and accuracy, they are expecting the answer is either yes or no. So they are very limited when you just decide it's yes or no. But for the search engine, actually what we care about is also the relevance. So the relative strengths, and this feature cannot be calculated inside the accuracy approach.
Yes, so now, what is ROC analysis? So basically there are graphs for visualizing the classifier's performance. So there's nothing more simple and intuitive than having the results on a graph. So, and on the graphs, we have the TP rates and FP rates plotted. So TP is on the y-axis and FP is on the x-axis. And then this works well with skewed class distribution. So that is the biggest advantage of this, and that's the reason people actually use it. So we'll see why it is in the next slides. And then curves in ROC. So there are two classifiers which have been discussed in the paper. The first one is the discrete classifier and the second one is the probabilistic classifier. So the way discrete classifier is plotted is you get a point with the TP rate and an FP rate, and that's just put on the curve, put on the graph. And then for probabilistic classifier, you have something called as threshold. So if any value you get is above the threshold, then you classify it as positive probably, and then all the values below the threshold are classified as negative. And by varying the thresholds, you get something called as a curve, ROC curve. So, and then we try to analyze area under ROC curve, so which will be covered by Rumi.
Yeah, so these are the graph you get from paper. So usually from ROC curve, we can draw the area under the curve. It's called a ROC convex hull. So basically, if a classifier's curve is underneath another classifier's convex hull, means this A and C classifier, which you have a higher or bigger convex hull, they will always are superior than B and D classifier. So the intuition is given the same false positive rate, you get the best true positive. That if a classifier can get a higher true positive, then we think that it has to be better than the lower classifier. So that's just intuition. But so given this convex hull, we can decide what are the better classifiers, and we can also decide what's the best threshold depending on the misclassification cost and also the classifier distribution. Because in the end, the cost is measured in a way like a totally wrongly predicted examples multiply each of the costs. So if you have the same cost for misclassification, but you have a lot more negative samples, then you want to choose threshold which is high, so which will be close to the 0 point, so that you don't really generate a lot of wrong negative example. On the other hand, so for like clinical data, so they usually don't want to miss any patient, so they require so they require you to have very good recall. So then you will choose some threshold which is a bit lower, so you can classify much more positive people or patients, even though they are false positive. So then if this ROC curve, we can calculate the area. So the way in reality they calculate is by updating each threshold how much area they increase using that kind of like calculus thing. And so this AUC is a number, and this number usually is independent. So this number is independent on the decision threshold, and this number is also independent of like a prior class. So it's very easy and very nice because no matter how you tune your classifier and how you tune your misclassification cost, you will always get the same AUC. And it also kind of indicates, like, given a positive sample, random one, how much chance this classifier really can guess or find out this is a positive sample. So for uniform classifier, or random classifier, the chance it gets right is 50%, so 0.5 for the AOC. And we are expecting any trend classifiers should have higher value than that, should perform at least as good as the random classifier. So why do we care about evaluation? So there are 3 points. One is we want to estimate how well our model performs. Then use the evaluation, we can actually try to find the optimal hyperparameters, so like SV and the cost parameter, or like a k nearest neighbor. K is the hyperparameter that we can actually use the evaluation to optimize. And then after we optimize the many models, we can also use the evaluation to decide which model is the best model for this type of problem or data. And I just want to mention, like, we also heard about loss function. So loss function usually refers to the function which is used, being optimized internally by the classifiers. So they are not always the same. They can be the same, sometimes they are not. So for example, for the SVN, the loss function is this red line, it's called the hinge loss. As we use this loss function, this property, to successfully find the maximum margin hyperplane, it has to use this loss function. But after you get the SVN classification label or output, you can do whatever kind of evaluation you want on this output label. Like you can use accuracy, precision recall, or even draw the AUC. But just keep in mind, so if your algorithm somehow optimizes on the value of your evaluation, then you can assume this is like the best case scenario for your evaluation. So for example, this algorithm is optimizing on AUC, and this is not. So you can see the rank booster always has higher AUC than the AUC split. Even though for accuracy, it doesn't really look like the rank booster. It's so much smarter. And then I found out, so after we talk about all the evaluation metrics, I found a paper, it's in NIPS. So it said that actually even as small as data set, I can always prove to you I can find a good solution as long as the data set is small. So that's the thing. So to have a really good evaluation, the test set where you are being evaluating should be representative and should not be too small and should not be really like biased. So now just...
Sorry, do you think, maybe this is a question to the class, like, do you think that this result is surprising, that there is always a classifier that does really well on small data sets? I think it's expected, and I didn't show the slides for this, but there are, for example, upper boundaries that you can define with the Vatnik-Scherer-Menkes dimension that basically prove that a neural network, for example, depending on the number of parameters and the power of transfer function and whatever it does in the neurons, that it can approximate anything as close as you want it to be on a compact interval. And so, like, a neural network is a universal approximator, it can approximate anything. And so it's not really surprising to see something like that. But there are also different classifiers that you can do this on, so yeah.
So in principle, if your classifier can memorize everything, even a small data set, you should perform well on that data set. So now, we also want to talk about actually evaluation is very application and data dependent. So for example, for machine translation, how would you evaluate for machine translation? What's the problem? Sorry. So what's the problem here? How would you evaluate? So I mean, I give you a foreign language, and this means today is a good weather, and now you need to translate this foreign language into English. How would you evaluate the translated text?
Get someone to listen and look at it.
You want a person to listen to your outputs all the time?
It's one solution.
Your girlfriend? I mean, what's the so let's say the thing why we can calculate accuracy is because we know the answer is either yes or no. And for the translated text, do they have this property? And if we ask annotator to write some translated target for us, is that good enough? We just compare the translated text and the translator's referral text. So let's say if I say today is good weather, can I say it in a different way?
Yes, the weather is
Yes, no. Saying the same sentence in different ways, and there are n number of possibilities how you will say that. And to analyze all those will be like not efficient, or it will take a lot of work. Kind of computing.
Exactly. So the problem here is exactly like the acceptable answers are too many because the property of language is meant to generate infinite concepts or semantics. And if you ask the annotator to write a referral text for you, they will write differently. It's even harder just to find the consistency between the annotator's referral text. So what they use usually, one famous scoring is blue. So they're actually trying to measure the similarity between the targeted text and the machine translated text. So they are trying to see which words have appeared in the target and how long does it appear. So kind of get the similarity matrix. Remember for the search engine, we think we already talked about it. So because the place where you propose the answers matter to the user. So when they optimize, they will optimize the best result should appear in the first. And then for the stock trading agent, would you just use accuracy to decide the agent algorithm, or what else would you use?
Basically, stock trading data keeps changing.
Yeah.
Like we spoke some time back also, like that we need to take into consideration at what time the trading was done and when we are trying to predict. So we need to take into consideration the time. Basically.
Yeah, the time is definitely important. But what's the most important things people care about in the end? It's the money, right? It's the total money. So it's not good enough to say, yeah, I get many prediction right. Each prediction I earn a little bit. Then you make one single mistake, you lose all your money. Then it still sounds a really horrible algorithm. So so it really, evaluation is strongly tied to the application, and it's more like you want to evaluate what people care about in this domain or in this application. And except for evaluate how good or bad or what's the prediction capability of your model, what are other criteria people might be interested in? Not just about the prediction capability, but more like, for example, like variance, people care about it. What else? You can think about like, if you really want to implement and use your system, what's the things people want to know?
Time performance, maybe like how much time does it take to classify, how much time does it take to train?
Exactly, so time matters a lot. And so timing matters. So like deep neural nets. Neural nets started very early, but it only started to get popularity in the middle of 2000. Because it's so slow to train, it takes weeks and weeks, and actually nobody really has patience to wait. I mean, I think just there are also like a training time performance, and then there are also like a prediction time performance. So what kind of algorithm you think it's probably you don't need to train it, but if you want to predict a label, it will take you a lot of time. Okay, I think this one is a bit harder. So for example, like a k-nearest neighbor, if you have 10 million samples there, And now I tell you, I find a new sample here. I want to find the top 10 nearest neighbor for this sample. What are you going to do? You are going to compare this sample against with 10 million samples to find the 10 best nearest neighbor. So
But
this
training didn't.
there's no training. So this algorithm doesn't have training. You just need to use the prediction time to find the predicted label. So that's something like its prediction time will be very low. And then another thing is about like a memory. So for nonlinear SVN, usually it takes a lot of memory when I'm doing a hyper transformation, kernel transformation. I think I saw my memory consumption was like 16 gigabytes when I was running nonlinear SVN. And it's also super slow because if you consume a lot of memory, they're going to swapping and it's probably not practical to run on your computer. So those kind of things are also interesting for other people to know, so they have an idea how long can they have to wait after the training and the prediction. And then the variance, people already talked about it. And then we want to ask, so there are some principles or like ideas like we should respect when we are doing evaluation. So one example is the test data set probably needs to be representative. And what else do you think that when we do evaluation we should keep in mind? Really? Okay, fine. So it's also important to choose your baseline because you are evaluating, you want to compare your algorithm against something else. So it's like you probably need to present the baseline performance, and usually it's either state-of-art algorithm or very famous algorithm. And also, you will probably tune your own model. So before you evaluate on other models, you probably also need to tune their models. So then it's compare against each other in the optimal situation. And if you have the need to propose your own evaluation matrix, like your problem is newly defined, nobody has evaluated anything before, then you probably also need to include like just basic accuracy or really well-known matrix layer, so that the other people they can quickly understand how well your model is performing. So that's all. The rest is not really important. Okay.
Awesome. Thank you.